So tonight we're going to be talking about ferrets, or ferrites rather. So
Hmm.
let's get this going here. Come on, it didn't do my usual stuff. I assume, let's see, are you seeing my PowerPoint?
Yes.
Yep.
Okay, so let me get it cranked up here. So they've changed some stuff on it. It's not showing the usual stuff. Okay, so are you seeing just, I don't, are you, you're not seeing the stuff on the side, are you?
Yeah, we're seeing the sidebar mic. We're not seeing the
Yeah.
Okay,
presentation full screen.
there we go. Does that look more better?
Yes.
Okay, okay, so it should say measuring ferrites with your nano VNA. So this is going to be a little bit of a practical class here on being able to use your nano VNA and figuring out what ferrites do for you. So we're going to be talking about some equipment not working correctly, how things get screwed up with RFI and a bunch of other noise and stuff. We'll talk about using ferrites for RF and reducing common mode current. So I always considered ferrites to be like a big RF sponge, and we'll see how that all works. So we'll talk about the most common type of ferrites. We'll talk about measuring ferrites, and we'll talk about best ways to use ferrites. It's pretty interesting when we get into that part. So let's first talk about a little electrical noise. So your transmitter for ham radio operators, that's kind of your number one guy that's always the culprit about making electrical noise there. So we also know that coax is a great conductor for electrical noise, getting into helping it to conduct uh, RFI around our equipment. We also have times where your AC line coming in, it can have a hash and noise on it from other industrial uh, entities that may be dumping some bad stuff onto your electrical stuff. Also, you find that there's times where you can be the source dumping RFI onto your AC in your house and it gets reflected on other pieces of equipment like your telephone. One person did for the court system did translation from tapes to writing documents for what went on in courts. And the guys, every time he keyed up, his transmission would always get wrapped up into that translation or that audio system. So he had to figure out how to end up taking care of it. DC power supplies noise. So like, switching power supplies, great place to end up both getting noise into and also for your transmitters when you're sharing power supplies across several pieces of equipment, and also propagating that noise through the connections on there. Control cables. We'll talk a lot about USB cables and how that can affect your operations. So here's a really nice picture of a bunch of different kinds of ferrites. You got donuts and you have flat ones like in the upper left-hand corner. So if you have like a flat ribbon cable, you can run it through a ferrite like that, and it will end up sucking up any of the switching noise that goes across that. You have clamp-ons kind of through the center, and you have little donuts, you have big donuts, and all kinds of other stuff in there. So that's some pictures so you know a little bit about where you're talking. So these ferrites, the black stuff there, and the green one up there, those that is all made out of a ferrous material. So it's built in such a way to soak up and to pick up and to interact with magnetic types of energy. So, for our RF, that's electromagnetic energy that we end up transmitting through the air, and these little devices are made to soak that stuff up. So let's talk about material that they use. It's quite a science to figure out how to end up building these materials, building these devices. And there's different kinds of materials and different kinds of properties that make it good for different spectrums and different parts of our hobby for as a ham radio. So there's four major there's zillions of different kinds of ferrites, but for ham radio operations, these are the four main ones that everybody always use. So one of the ones that I use almost all the time is that mix 31. So that mix 31, the properties in that ferrite is good for soaking up RF energy between 1 megahertz and 300 megahertz. It's a good general purpose ferrite. It's good for coax and HF type of frequencies. You know, most of my life is spent on HF, so this covers that entire band quite nicely. Mix 43, that's probably the most common ferrite that you're going to find any place that you buy them or trade them or find them. But those guys there, they're really for the higher part of HF bands. So are good for soaking up energy between 25 megahertz and 300 megahertz. So that's like, you know, getting into 10 meters, 6 meters, 2 meters, 440, that kind of area there. Actually, it doesn't quite get into 440. So it's the higher frequencies that it gets into. But it's also does that one there does a pretty good job of dealing with hash, RF type of hash. So this is just kind of a mixed potpourri, yeah, something like that. Mix of different kinds of noises that can travel across some conductors. Some of the special ones, like if you're dealing with VHF, UHF, is your mix 61. That's good for 200 megahertz all the way up to 2 gigahertz. So if you're working really high stuff, high speed stuff, that's high frequency stuff, that's a good mix for. Then you have another specialty one, which is for really, really low frequency, and that's the 75. I personally have not used any 75 mix 75 stuff, but that's good for like 1.5. So that's down below the AM band, all the way up to 10 meters, which basically covers through your 40-meter band. So that's very low frequencies. And sometimes guys like using these on amplifiers, trying to get rid of any RF that's creeping out of them. So whenever you hear mix and ferrites together, it stands for the concoction that they mix up to make the ferrites. And these are the various numbers here that we commonly use for ham radio operators. So when you're trying to track down some noise that's causing you problems and that you need to use ferrites, and goes with on along with any kind of uh, of noise, but you always want to identify the source. Where is the source coming from? You want to try and figure out, and this takes a little detective part, figuring out the path of how it's getting to something that is where it's causing the problem. And then the third thing is you want to know the frequency range of that. And a spectrum analyzer, there's other equipment like a spectrum analyzer that is good to help you figure out. Some of it you can, like frequencies and stuff, you can figure that empirically because you know what frequencies you're transmitting on or operating on. If it's an external source that's getting into you, then you may need a spectrum analyzer to try and figure out where it's coming from and what the frequency range of where it's causing the problem. So once you figure out source, path, and frequency, then you go about selecting the right mix and from the previous sheet, the what kind of ferrite, and you want to figure out what kind of shape that you want. Is it going to be a slip-on where it's going to just slip over the top of coax? Is it going to be a clamp-on where you kind of clamp it over the coax, or is it going to be a ring where you feed the wire through the center of your ferrite? So those are the three major kinds, and you have to kind of figure out how you're going to end up using that. And we'll get into a little bit more of that a little bit later. So, so your equipment's not working right. And so what do we mean by that? So every time I transmit, the display on my radio gets scrambled. So it gets all torqued and bent out of shape. Or my radio hangs. Or my PC reboots. Or you have programs that freeze on it. So this is, you don't always have, you can have some of these problems if you're even just running 100 watts. It's not uncommon. But as you start moving up the scale and start running more and more power, these kinds of problems become more and more, and they become more difficult to try and mitigate. So generally, when you have these kinds of weird behaviors there, where your radio's not working right or your PC's not working right, the first thing you always want to try doing is improve the grounding. Improve the grounding. There comes a point where you get to diminishing returns where you can't really improve the grounding that much and that much more. You've done everything you can. So once you kind of pass that benchmark, then you'll look at using ferrites. You're a good old RF sponge to try and soak up some of that energy and prevent it from going anywhere. So, blah, 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 blah. We've already talked about some of this stuff here. Main thing is like control cables and USB cables. We'll be getting into this a bunch here in a little bit. So what I did was set up some experiments. So what I'm going to be trying to do is show you what's different kinds of configuration of ferrites, what is going to happen there. So I used my good old trusty Nano VNA, which the price point on these guys is that's probably the number two thing that most all of us hams want to have is some kind of a antenna analyzer. So for some people that nano VNA is more than what they can handle. Other people learn to use YouTube to walk them through how to set it up and to run it. And other people are accustomed to operating a big um, VNA or spectrum analyzer, and all of that comes straight across in how you operate that nano VNA. So what I did here, so just to keep things simple and straightforward and non-complicated, I calibrated. That's always the first thing you do with a VNA. You calibrate it. So I calibrate it for 1.8 for 160 meters, all the way down to 30 megahertz, and that covers 10 meters. So 160 meters to 10 meters, 1.8 megahertz down to 30 megahertz. So that's what I calibrated. So I set it up. So I did the format of doing pass through. So whenever you see S21, if you look down at the VNA, the bottom port, so what I'm going to be doing on this on port 2, I'll be transmitting out of that port, and I have a reference signal of 1 dB. So 1 dB is going out that port 2. So it'll be going out, and you can see my little alligator clips there, and I'll be clipping onto some wire, and we'll be measuring how much loss, how much that 1 dB signal gets attenuated. So that signal comes back in on port 1, and it's displayed on as a reference signal. So that's that little yellow line. You can see the second line down on that display. There's a 0 off to the right side. That is showing when I have a piece of wire that has these two guys clamped together. So that shows a flat line all the way from 1.8 megahertz to 30 megahertz, and that's the reference signal coming in there. And so what I'm going to be doing is measuring how much below this line in dB, how much energy of that 1 dB signal is going to be absorbed. I think hopefully everybody got that. So what I did, I could have set up a whole bunch of markers around here, and it just would have cluttered up the screen. But to keep things simple, all I did was set one marker, and you can see on the screen here, on that yellow line, it's a faint yellow line, a 1 there. So that's marker number 1. That's set at 7.22 megahertz, the 40 meter band. And that's just something we're going to be using as a reference point on how well this ferrite is doing on sucking up energy. So here's the first test that I did. Over here on the left, that's one ferrite. That's one pass of the wire. That blue wire is one pass. So that represents every time wire goes through the center core of this thing, that center hole, that represents one turn. So you can see with this ferrite, as I remember, this is a 31, so it does a pretty good job of taking care of the HF frequencies. So you can see with my marker there, number one, that's dropping the signal. That's the wrong, oh yeah, it's dropping the signal at that marker M1, 7.22 dB. I have 7.2 at the top, so I screwed up on something there. So, but basically one turn drops you 7 dB. 7 dB, that's not a whole lot of loss, but I mean, it does a little bit of work. And you can see as the frequency goes up, it gets all the way down to about 10 dB. So let's try and see what happens when I add two of these ferrites here. So I have two ferrites, one turn going through each one of these guys here. Here you can see the loss has now gone to um, a 9, yeah, minus 9 dB. Did I say something? I think I said something backwards. No, this is wrong. It's wrong on what I have up here at the very top of it. It should have been the loss of 5.7 dB, loss of 7.7 dB. So that's a loss of 5.7 dB off of the 0 dB reference. So we're always going to the negative thing. So I screwed up on the labeling up at the very top. Mind you, this is the first time going through these slides, so um, you know, you know me, I'll have some errors in here. So with two guys in there, it gets me to a loss of 9.4. You can see that it's not linear. It's not doubling the loss. This is 5.7. This is only 9.2. So it's maybe a third more, but it's not a two times factor. So let's go for three of these ferrites. Here you drop from the 9.4 to 11.9. Not a whole lot of loss there, but it is more than what you had before. So you can see that just stringing these things along doesn't always get you what you want, but you can see it is pulling down the loss on there. It's sucking up some of that RF. So let's go to another example. This is one ferrite. You can see it's a 31. It has three turns, so the wire goes through the center of that thing three times. And whoopie-doo-dah, we went from 11.8 dB all the way down to 20 dB. When you start getting in that 20 dB worth of loss, you're talking about some serious attenuation. So it's doing a really good job. That's like if you have a really ugly problem and you really want to nail it, you want to get into that 20 dB worth of loss. So what have we found about this is that, you know, if you could have the ability to wrap that cable through a ferrite multiple times, you can get some serious amount of attenuation. Now this hole here is only like about 3/8 of an inch. If you went to a different style of ferrite that maybe had a 1 inch hole through it, you could get a lot larger cable multiple times through it. So you have to think about what cable you're dealing with, how many loops you want to go through it. When you purchase the ferrite, you want to buy the appropriate size for it.
Hey, Mike,
Yo,
is there a way to determine how much of that is induction versus from the ferrite?
um,
I mean, you're making a coil there, so that's naturally going to resist.
yep. Um, there is, it's not that straightforward. Uh,
Okay,
but you know, you do have some EMF that is basically cross coupling that, and that may be canceling some of it out. But typically, if you do that, the wire has to be going in the opposite direction, not in the same direction that it's going.
Mike,
Yeah.
excuse me. Well, first of all, yeah, I believe it's an inductive effect. In other words, it's inductive reactance and not absorption of electromagnetic energy by the ferrite, and the ferrite's losing it as resistive losses, which would be like tangent delta type losses, heating. In this case, if you've got three, I think you said with one turn, in other words, when one pass of the wire, it was about 9 dB
Hmm.
loss, and now with three turns, it's
7
about
dB.
20 dB. Is that correct?
With one, it was 5.7 dB of
Oh,
loss.
well, because I was thinking, because the inductance goes up as the number of turns squared. So three turns
Hmm.
would be 10 times the inductance of the one turn. In other words, the one pass of wire. But then I would think would go from about, if it were 9 dB to 20 dB, that would be a 10 times increase or increase in the loss due to inductive reactance. So if it's going from 5 to 20, I don't know if I can account for that fully by just pure inductive loss.
Nope.
Yeah. So
No,
because a lot of these
you
ferrets for
can't.
AMI, they rely on there's the permeability is complex. The
Hmm.
real component is related to the inductance, the magnetic effects, and the imaginary component is related to loss effects. Absorption, and then the energy being used up and trying to make the molecules not vibrate, but move, and heating up the core. So and I think
Yep.
most RFI and EMI, that's they choose the material based on that effect, not the inductive reactance effect. So there might be, I haven't
Hmm.
seen what number 31 mix, the characteristics for 31 mix yet, but I was trying to look that up. So okay.
Yep. So, so what you know, there's a lot of things in play here, but what I'm trying to really show you is that when you wrap it through there like 3 times, you get a very substantial um, reduction in signal that's coming through that thing. So let's go for the next step up on that. So here I'm taking two ferrites, each one with 4 turns going through it, and two of these in series. And here we're getting all the way up into minus 30, 31 dB worth of loss. So, and also you notice that with that second one, that slope here has really changed on how things look. So it's a different kinds of slope when you add the second one in there. But the point here is that when you sometimes the size of the ferrite, you can only get so much wire through that, and if you need to put more loss in there, more energy soaking, you end up having to add maybe 2 or 3 extra ferrites or doing the same number of wraps through it. So this is how you really get rid of some really stubborn stuff. Like, when I'm running some serious power, that RF gets into every single monitor that I have and scrambles things, gets into every single USB cable, and I have a ton of those things. And so many times I have to use 2, 3, and 4 ferrites in order to null out all the RF that gets into everything. Okay, so that's you're dealing with these clamp-ons here. Another one type that I really like using, and that's these ring type ones, these donuts. So just taking, and this is a 31, yeah, 31. And so this is with a number of, I think this is 7, 1, 2, 3, 4, 5, 6, 7. So, with one turn, it's really puny. Just passing a wire through something like that, because there's a lot of open space, you got to get the wire up close to the core material to get a good reaction from it. So just one piece of wire passing through it, 2.9 dB is doesn't do anything, but it starts moving up pretty quick. You get um, for 3 turns, you get 12 minus 12 dB. For 7 turns, you're 25 dB. So it's a whole lot of stuff. So these kind of cores, like a lot of times I'll use these for power cords and also like HDMI cables. These work really, really nice for the bigger, fatter cables to try and suck up that RF energy. Where back on these clamp-ons, these are better suited for smaller cables like your USB cables. Okay, so here's just a couple of things that I tried just screwing around with things. So I took one of these rings, ran 3 loops through it one way, and then 3 loops back another way. And this guy here um, gave me a minus 20 dB worth of a loss there. Not bad, pretty decent. Now, if I did it straight without this stupid little loop here in the center, I would have got minus 23. I would have got a little bit better response out of that. So here's something kind of interesting, and I imagine Scott can maybe explain this one. But if I take that wire and rather than ducking it through the center, but if I run it over the top and bring it up and around and make a couple loops, this configuration here, it only gives me about 1.5 dB of loss. Not good. So do you have, so Scott, do you have a reason on why that works that way?
Well, I have to really look at it, but I would say, if anything, that you got the winding on the left, maybe in the opposite direction of the winding on the right, and the magnetic fields are canceling each other to some extent.
That's right. That's what
Yeah.
it's doing. It's canceling. So just beware that as you're wrapping these things, I found one guy that had done this, and he wasn't getting any kind of response out of his ferrite there. But I don't remember the reason he did it. But when I saw that, I said, well, that's kind of weird. So I wasn't sure what it was going on. But when I rewound the thing, so everything was going in the same direction, then all of a sudden it fixed the problem. So here's a couple practical, or I got a couple slides here, some practical examples. Up here in the upper left, this is a power cable. Power cables, you like to end up putting the ferrite right up next to where the power is coming off of your radio and stuff like that. So this one here is a 2-inch core, 1.4-inch interior, and you can see the way the guy has everything wrapped around there. The one over on the right side here, the black and red wires, you can see where he's done the same thing. It helps to keep these things tight as you possibly can. Get the wire as close as possible to that core and keep it there. And using tie wraps to hold things in place as you wrap it. And when you need to hold things so they're really close to the core, using tie wraps really does a nice job. Down the lower left, these are actually no, these are clamp-ons, but you can use these as slip-ons. Slip-ons are cheaper to do it this way. But you can take a piece of coax and just slide on a bunch of your ferrites there, and then just put connectors on both ends of it, and that's way a lot of inexpensive type of RF chokes are made. And this is pretty inexpensive to end up doing and making work here. But it, but the key is here is that this isn't getting the benefits as far as having that cable wrapping through it multiple times. So this is nice. There may be a reason, but this is not going to be as anywhere near as effective as, like, let's say the one above that, where you're wrapping it around the ferrite multiple times. Over here in the lower right-hand corner, that's very typical of what you do. USB cables are kind of a number one nemesis as far as getting the RF into it, and it really screws up your radio and screws up your PC that you're talking to it. So you just don't grab one of those clamp-ons and run your USB cable through there one time. You want to get as many loops in there as you possibly can to end up knocking it off. Now, one thing I'll mention here is that ferrites, they don't stop the RF, they attenuate it. So all the stuff that I showed you, there, those are what happens when it attenuates that signal. So you still have RF energy getting through. The fact is, can you get that RF energy as low as possible so it's not interfering with things? Over here on the right-hand side, wrapping coax cable. This is a much more efficient way of getting a good attenuation. You can see he did the technique where he took that wire and ran it back through the center and under it and back up again that I had previously showed you and continued to take and wrap it around there. So that allows the cable to all come out at opposite directions rather than the cable, everything bunching up and coming out, both the innie and outie cable coming off in one direction. So that's the benefit of using that dipping through the center, whoops, and bringing it out the opposite direction. So you can keep track of which end of the cable you're looking for. Um, one on the left side. So one of the things you can buy is kits. There's a lot of kits out there for a radio. And like for beginners, a lot of times they don't know where to start on trying to track down RFI problems. So rather than trying to figure out where it's coming from, you use the old throw the spaghetti against the wall and see what sticks. So you can buy a kit that has a whole package of ferrites, and you can use it for wrapping around all your cables going in and out of your rig. Everyone that's going in and out of your rig to try and stop it. So that's one way of just knocking it down, and hopefully you guessed right and got enough ferrite on any particular conductors to make problems go away. So let's talk a little bit about
Hey,
price.
Mike,
Yeah. Mhm.
Ted was asking a question here, and I had some kind of a similar question. So, like on this choke, how does that impact the center conductor versus the outer conductor? Um,
It
as
does,
far as attenuation.
yeah, it does not affect the center conductor. It only affects the outside of your coax. Your outside of the coax is the one that's most commonly getting all of the interference that is traveling on, not the center conductor.
So the outer conductor is kind of protecting the inner one then.
Yep.
Mike?
Yeah.
Yeah, I just wanted to, for Ron's question, yeah, the conventional explanation for that is that the shield is due to the skin effect. There's an surface of the shield, the inner surface of the shield, and the common mode current is flowing on the outer surface, and it really doesn't see the inner surface. And the inner surface is actually coupled to the center conductor. So the idea is that you've got differential currents flowing on the center conductor and on the inner part of the shield, and those are equal and opposite to each other. And as long as if those currents are flowing in opposite directions and the magnitudes are equal, the magnetic fields from those will cancel each other. That's why coax is not supposed to radiate. But if you've got common mode current flowing on the outside of the shield, then there's nothing to compensate that, so therefore that will radiate. And not only radiate, but you can
Mhm.
induce common mode current, and that's how we pick up noise and things like that. So that's why the inner conductor is not affected, as long as the shield is good. If it's a crummy shield, of course, it won't work as well.
Yeah, well, and there is a lot less surface area on the interconductor, so that does
Right.
make a lot of sense.
Well, that's the conventional explanation you'll see in a lot of textbooks.
Yep. So because that outer conductor that shielding can actually both radiate and it can also be the source of RF energy getting coupled into that coax and then being transmitted along the outer shield. Okay, any questions there? Okay, so let's look at the painful part of it. So the cost of ferrites for the last probably 4 or 5 years last 3 years has been really painful, really moved up in price. So for that mixed 31 ring 2.5 inch one, it's going to cost you basically $10. For those darn snap-on ones, for a 1 inch diameter, that's the big, not the 3/8 inch, but this is the big open diameter that you can run power cables through. Those dudes will end up costing you almost $20. The mix 31, basically it's about $1 to $2 less as far as the cost. So far as the 43s, they're cheaper there to build, evidently. So one of the things that I do is that I buy in bulk where I'll buy a kit. So I just say, okay, I come up with $100. I'll just buy what I can for $100 and I'll buy a bulk, a bunch of those things at one time. And most of these things, like if you buy 10 or more, they start knocking off the price a little bit. You can also buy kits where it's a kit that has a bunch of different kinds of sizes and fits on it, and you can also reduce the price there. The Valley Radio Club, once a year, in fact, they just advertised that there's a guy that you can book a request with him, and you can say, I want to buy so many of this and so many of that. And then they go out and make a large wholesale buy to get a large quantity of these, and then sell them off to all the people that end up putting in their money to take and do the purchase. So they're not cheap, but it's like a lot of things, you can't get away without them. You got to have something in there to take and fix RF problems, or all it does is ruin the fun that you're going to have out there trying to chase all that rare DX and running those contests. So let's wrap it up here. So like any tracking down any kind of problems, you always want to figure out what the source of it is, where the nasty stuff is coming from. You want to figure out what frequency is, and then the type of interference. So that'll give you some clues on what you want to buy for the right kind of mix based on frequency that needs to be blocked and sucked up, absorbed. And you want it the right shape of ferrite that you purchase, either be a slip-on, snap-on, or a ring type of ferrite. So those are the things that you kind of need to know before you jump off and make your purchase there. It also helps, I guess, another one I bullet should probably put in there. You need to know what kind of cables this is going to go around. So when you're figuring out that source, what the path is that it's taking, you know what kind of cable it is. So you need to know the size of the ferrite that you need to end up buying, the physical size for wrapping around it. So for better rejections, get as many turns of wire or cable as possible on the ferrite. So just as many turns that you can wrap around there, the more turns, the better it's gonna work for you. So, and also, some of these ferrites, like when you get into bigger cables, like power cables, if you have like a 220 cable feeding your amp, that's not a small thing. So you have to end up sizing up to some pretty good sized ferrites. And many times on something like that, because of all the power that's going through there, you do end up needing to step up to multiple ferrites in there. So that kind of wraps it up, guys. And so, any questions you want to throw my direction?
Yeah, one I have is so if you go up to the table at the Hamfest and see one just sitting on a bench, any way of telling what you're getting?
Nope, nope. So they better have a really good price. Now, there's another program that I'll probably do on this subject, and that's using your nano VNA and going through there and testing your ferrite to figure out, well, is it a 41, or excuse me, a 43, or is it a 31? Or is it I don't know, whatever else that I had up there. So there's another little program I can do to take and show you how to end up testing that use. I think, okay, here's another one. If you're kind of interested, there's also there's at least three or four different YouTubes out there that you can watch, and it'll show you how to use a nano VNA to figure out what kind of mix you have.
Hmm.
Yeah.
Swiss Army knife of tools, huh, Mike?
Pardon?
A Swiss Army knife of tools, the Nano
Oh,
VNA.
you betcha. I mean, that is such a cool tool. You know, if with a little bit of understanding of RF and how some of that stuff works, man, that Nano VNA is just so cool in what it can tell you.
Right.
Yeah. So,
So yeah, I mean, I've initially learned how to wind some nice ballons and onions, and basically, common mode chokes on a very good video called the series is called TRX Lab, and I don't know if you've heard of it.
mhm.
It's a German guy. And
Oh,
he is a ham plus a RF engineer, and he has fantastic videos on lots of things. So he has several on doing one-on-one types of chokes for transmission chokes and other types of balance or unknowns like 4-to-1, 9-to-1, etc. But on the common one choke one, the one-to-one, he shows you how he doesn't use a nano VNA, but he uses benchtop VNA. And you could easily, and I've done this, I've just taken my Nano V and just basically copied what he did. Shows you how to set it up, how to wind the thing, and then be able to inject the common mode current into it, and then see, what the suppression is, just the way you were showing us, with
yep.
the log mag display.
Hmm.
And then you could see, and he's saying, what you really need is you want at least 20 dB suppression of common mode from 1.8 megahertz all the way up to 30. And so his actually it wasn't his technique. It was another German ham who developed the winding technique, and it really works well. And then he took some these types of chokes that are on the market people buy, and he was measuring those and showing that they're not what they're advertised at all.
No,
Just
they're
did not,
garbage. They're
yeah,
garbage.
they are. So anyway, yeah, there's a lot. It's very easy to do, really. It's not hard. If you've
Yep.
got an NOVNA, it's very easy to do the measurement. So I would be very interested to see what you have to show us on that. And if you want to wind your own chokes for transmission, this is very good. And by the way, last month I bought four 2.4 inch number, I think it was 31 mix of Ferrites from DigiKey for $7 a piece. Okay, so I
Good.
deal on that.
Yep.
So the prices may vary, but yeah, I always keep them around. And by the way, yeah, if you do a one for transmitting, not this is for receiving and for low power stuff, but for high power stuff, you got to talk about the maximum flux density that you can put through these things before they'll saturate. And a lot of people
Yep.
make the mistake of using putting way too much power through something that's really meant for much lower power densities or powers. And like, for instance, they'll put, 500 watts through something that really should have only had 100 watts. And then you're getting all the saturation effects and then the thing's not working at all.
Hmm.
So that's it's important to keep in mind. So if you do another program on this, it would be really interesting to talk about that stuff.
And actually, you can get to the point where your ferrite stops working.
Exactly. It'll turn into a capacitor,
Yes.
basically, yeah. And not just the capacitor, it'll just saturate and then it won't have any inductance at
Hmm.
all. The
Yep.
core won't work anymore. So the inductance drops to like a rock and then it
Yep.
absolutely has no choking power whatsoever.
So we also like for 7QP, we found that I acquired some really honking big ones, but the energy that we bring in off of our generators into our warming hut, um, we got in there with a micro or nano essay, and it was quite a bit of noise we found coming in on the wires from the generator into our hut there. So we went through there and out of the generator. I put on these big clamps, ferrites, and coming into the warming hut, put on some more, and substantially reduced a lot of the hash that everybody was dealing with. In other words, if you're out in the wilderness, nothing else around, you should not have an S5 noise level.
Right.
So it's time to start because you cannot, like on single sideband and any of the normal stuff except for FT8, you cannot copy a signal that's below your noise floor. So if you have a noise floor of an S5, between S5 and S0, there's a whole lot of other signals that exist there that you're not going to be able to listen to. And so by using those ferrites, that did end up substantially helping things. Didn't get rid of it all, but it did help.
I remember that, Mike.
Yeah, you were partner in crime there.
Yes, sir. And the other thing that was also worth mentioning is we gave the main power cord into the warming hut its own passageway and kept away from all the coax and did not run it parallel. And so that also reduced it even more as well. So, but yeah, the ferrites were a tremendous help in getting the spikes out,
Yeah,
the high noise.
that was a whole learning process as far as
Oh,
keeping
live.
keeping that power cable away from all the coax. It had to have its own special entry coming into the hut there, and then adding the ferrites to take and make sure that we did not distribute that generator noise across all the other components, all the other radios. Anything else?
Great presentation,
Thank
Mike.
you.
Lots of learning there. We all walked away with something, I think.
Well, next key is what are you going to do with that information?
Yeah.
It has to get turned into action.
No.
Okay, folks.
All right.
Back
Well,
back to net control there. Back to
yep.
you, Paul.
Thank you. Thanks again, Mike. Always a pleasure hearing about all the things that you've learned or picked up along the way or researched. Very, very valuable. Thank you very much.